Hello, everyone. Today we're going to be talking about some applications of entropy for real chemical systems and physical changes. So let's go ahead and pick up a little bit where we left off last time by talking about how entropy changes for a expansion or compression of a gas chamber. So again, this is our classic old favorite. So let's go ahead and start with an isothermal expansion. So again, we typically really like describing isothermal expansions and compressions when talking about entropy, simply because when I'm dealing with an isothermal system, this really helps simplify my description of how temperature and heat are related. If I have an isothermal system, I don't have to worry about temperature changing along the path of the heating of my system, so that these two can actually be integrated separately, which again, keeping our integrals simple is almost all what PChem is about. So under these scenarios, the reversible heat of the isothermal expansion of a system is actually fairly straightforward, as we already proved it to be given by nRT ln of the ratio of the final over initial volume. So when we turn this into an entropy-driven expression, the t's just cancel out, and we actually have a fairly nice description of the entropy increasing or decreasing with an expansion or compression. For example, if I see a compression of the system and the volume decreases, the final volume is less than the initial, and this means that the natural log of the ratio will give me a negative value, and I'll see a decrease in the entropy of the system. Because as I compress the system, I'm taking away the options for movement. If I have an expansion, we'll see a positive increase in the entropy of the system, as there's going to be many more microstates or configurations for my gaseous system to adopt. And one of the nice things is that while we've proved this for a reversible system, this reversible heat is part of the definition of the entropy of the system. So this actual expression is going to be true for any isothermal system. So any sort of isothermal expansion or compression will always have this description of the entropy of the system. However, where reversibility becomes quite important is when we're talking about our surroundings. So our surroundings are going to have an entropy given by the heat of the surroundings divided by the temperature of the system. But it's worth noting that the heat of the surroundings is only going to be equal to the reversible heat under reversible conditions. There's only going to be equal to the negative of the heat of the system under reversible conditions. However, under these reversible conditions, we do get a quite powerful relationship, as the entropy of the surroundings can simply be given as the negative of the entropy of the system. And again, we can then plug this into our description of the total entropy, which again is what dictates favorability. And we find that the entropy of the system plus surroundings gives us a total entropy of 0, which again is really our definition of a reversible system, and that this expansion or compression could go either way if it's reversible, which again makes sense because it's occurring slowly enough that at any given point, either direction of movement is possible. And again, this is an important consideration when we're talking about reversibility. However, not all expansions are going to be isothermal or are going to be reversible. So we have to watch out for how the entropy of the surroundings may end up be subject to change. We can look at essentially another extreme condition, which is free expansion. So if I say go ahead and remove any force trying to dampen the expansion of the system, I'm not trying to get any work out of the system. Well, since it's isothermal, we know that the internal energy is going to be 0. Since I have a free expansion, we know that the work is going to be 0. And since the internal energy is equal to 0, this means that heat is equal to the negative of work, which in and in itself is also going to be equal to 0. So again, taking a long circle around, since the heat of the surroundings is essentially going to be 0, there's going to be no heat flowing into or out of my system from the surroundings. This means that the entropy of the surroundings are relatively unaffected. So when we're looking at this in terms of what's happening on an entropy perspective, my system is going to become more disordered as it expands and it's occupying a larger volume. But it has no interactions with the surroundings. So again, all entropy change is going to be in the system and not in the surroundings, which gives us a total entropy of nr natural log of the two volumes. So what this actually ends up doing, especially when we pair it with our reversible expansion, is indicate some rather cool features. So we know that the minimum entropy of the expansion of an isothermal system is going to be 0 if it happens very slowly, and I am essentially decreasing the entropy of my surroundings as much as I'm increasing the entropy of my system. However, on the opposite extreme, we have the maximum the entropy of the universe can increase is going to be based on the increase of the entropy of the system, as the surroundings are left relatively unaffected. And so what these two cases do is they kind of help us set boundary conditions on how much the entropy of how much the total entropy can change when I have an isothermal expansion. And indeed, you can actually apply a lot of these same ideas to non-isothermal systems, though it is worth noting that the integrals become a little bit more messy, and you'd have to be very careful with how you're addressing that temperature change. However, it is indeed possible and is quite an impressive task to try and accomplish. However, there's also many other sorts of physical processes that we might care about. And one great example is our good old-fashioned phase change. So let's go ahead and say that I have a solid that is well organized, and I want to go ahead and turn it into a liquid. Well, let's go ahead and try and examine this process. Now, most phase changes are typically going to occur as isothermal processes, as the temperature of the substance really isn't changing, just its phase or identity. And so this entropy of transition is going to be inherent in the process. In general, we find that a liquid is going to be more disordered than a solid because there's many more configurations that the individual molecules can take, and a gas is even more disordered. So we're going to generally be seeing positive entropies of transitions as we go from solid to liquid to gas. And it turns out that we can actually, so this entropy value won't be very variable. However, as we saw previously, we're going to see a lot more flexibility in the entropy of our surroundings. So the entropy of our surroundings is usually what we have to monitor when we're trying to determine whether the process itself is favorable. Because while this value is relatively fixed, this one can have a number of forms. And so it turns out that the entropy of our surroundings are going to be dictated by two major features. First of all, how much heat is being released from the surroundings to drive the process. For example, if I'm going from ice to water, this typically involves bringing in heat from the outside. So the amount of heat is going to be very crucial. In addition, the temperature of our surroundings is also going to make a difference. Because again, if my outsides are very cold, they aren't going to want to lose the little heat that they have. If the exterior has a lot of heat, has a high temperature, then well, losing a little bit of heat will be a small price to pay. But again, because we typically don't measure the heat from the surroundings, we're going to essentially phrase this in terms of the value of the heat required to drive this transition, which again is just going to be the negative of the heat of the surroundings, because in any energy gained by the surroundings is lost by the substance undergoing transition. So what this does is it allows us generate a new alternative phrasing of how the total entropy of my how my total entropy changes in terms of the entropy involved with the transition itself and the entropy of the surroundings. Again, now exclusively in terms of the system itself, because we now have it phrased in terms of the entropy of the transition and the heat required to drive the transition. However, we often don't want to work in the infinitesimal notation, so we often want to go ahead and integrate this for the whole transition itself, which, as we've seen previously, is a bit messy for a non-isothermal system. But for an isothermal system, this temperature is going to be a constant value. So we get the change in the total entropy is going to be equal to the entropy of my phase change minus the heat required to drive the phase change and the temperature of my system. Now, again, we run into some slight issues here because heat is a path function. And it turns out we really hate working with path functions. So in order to try and turn this into a true state function, we're going to need to constrain our system a little bit more. So one simple method of doing this is to constrain it to an isochoric change. So essentially, this would be the idea of I have some water, I lock it in a can, and I freeze it. Well, you've seen how well that, anyone who's seen a busted pop can knows about how well that handles. But if you proceed under this, under these constraints, we're able to turn the heat of our transition into the change in internal energy of our transition, which again is rather nice as we can actually locate many of these values in the literature. However, we're not typically chemical engineers. Instead, we're chemists. So instead, we often work under isobaric conditions, and my heat becomes the change in enthalpy of a transition, which we've already developed a good set of descriptions of how to try and find the enthalpies of phase changes. So this is a very nice way to approach the problem. However, if I go ahead and lock, say, my water away in an adiabatic or insulated container, well, then it's actually fairly simple. Of the entropy, the total entropy change is going to be equal to the entropy of the transition. So again, this is seriously going to limit what sort of processes can actually happen if there's no heat to release into the surroundings or to extract from the surroundings to help drive the process forward. Now, typically, we're going to be looking under these isobaric conditions. And we typically really like to make use of this set of equations because this is this is a good way to try and figure out whether a reaction is going to be favorable. Again, a positive total entropy indicates the reaction is possible simply by knowing the intrinsic entropy of transition and an enthalpy of transition that we can look up in the literature. And then the only value that is going to be highly flexible is going to be the temperature itself. But there's also another very useful thing that we can do with this equation, which is make use of reversible conditions again. Because under reversible conditions, so this is when my phase changes at equilibrium, my total entropy is going to be 0, which means that the entropy of my transition or the enthalpy of my entropy of my system is going to be equal to the enthalpy of the transition or phase change divided by the temperature. So this is one of the reasons why reactions, phase changes are typically only reversible under a certain temperature at a certain temperature. So for example, if I'm looking at the fusion of water, so water, ice melting, it turns out that this transition takes place at 273.15 or 0 degrees Celsius. Gotta love those numbers. So we can go ahead and use this temperature along with the enthalpy of transition that we previously determined when looking at enthalpies of reactions to determine the entropy uh, of the melting of ice. So we know that the enthalpy of transition for melting of ice is uh, 5, 5.06 kilojoules per mole. Again, this should make sense. It's a positive value because it takes energy to melt ice. And we know that this reaction becomes favorable at essentially 273, which gives us an entropy of the system, or the entropy of the phase change, of 18.5 joules per mole Kelvin. One of the things you should watch out when going in between enthalpies and entropies is to make sure to watch out for the units. So as entropies are typically presented in joules per mole Kelvin and enthalpies in kilojoules. Now, again, one of the things I kind of want to point out is the why this temperature of equilibrium essentially occurs. Because the melting of ice essentially requires a certain amount of energy. And if I'm hotter than 0 degrees Celsius, it's very entropically favored to lose a little bit of energy from my surroundings because they don't mind, and to use it to drive this entropy favored process. However, if I'm below that temperature, it turns out that the loss of entropy of losing that heat from that cold surroundings is going to actually be much greater than the entropy gain I get from transitioning phases. So one of the important things to think about when we're talking about whether a reaction is favorable, we're essentially balancing how much am I ordering or disordering the surroundings, which is really what enthalpy tells us, versus how much am I ordering or disordering my system, which is really what the entropy of a reaction tells us. So this is something very important to keep in mind as we go forward. However, what we've kind of done is we've dropped the elephant in the room, which is the realization that entropy itself, both transition uh, and of the system, is going to be, to a certain extent, temperature dependent. So we're going to be looking at entropies of temperature change a little bit more next time. Till then, take care.